All right, good afternoon, everybody. I'm Joey Echevarria. I'm going to be talking to you about some streaming ETL. Before I get started, if you're interested in grabbing a copy of the slides yourself, they're already posted online. You can download them, view them there. If you want to take pictures of slides, this is really the only one that you need a picture of so that you have that link. Leave it up there for just a little bit longer so that folks can capture that. All right, looks like most everybody's got it. So I'll give you a little bit of background. For starters, I work for a company called Rakhana. We do IT operational monitoring. So we collect all of the logs and metrics that your systems produce. We do it at massive scale. So we're usually collecting all of the logs from all of your data centers, not just one particular application or one particular distributed system. We're really after all of it. We do that as on-prem software, so we go in and we get installed on your environment. And we're built on top of a big data stack. So we use Hadoop under the hood. We use Hadoop SQL engines, Hadoop file formats. Pretty much all of your data is in an open source file format in our platform. But then we've got a mix of open source and proprietary components that actually do the data collection and analysis. And a big part of that is stream processing. Logs and metrics are always coming in as streams, and so you need to process those as they're being produced. So specifically on me, I'm Rakhana's platform technical lead. I'm basically responsible for all of those open source and other components that live in that sort of stream processing stack. I used to work at Cloudera. I was there for about 4 years. Before that, I was at the National Security Agency. And historically, I've worked in distributed systems, data security, data processing, big data, all the good fun buzzwords. I also wrote a book for O'Reilly called Hadoop Security. So if you're interested in that, you should go ahead and check it out. So some history on stream processing and the kind of data architectures that we apply this to. This is what I call a legacy data architecture, which is really funny because this is not that old of a data architecture. A lot of people using Hadoop systems will have data producers. They could be databases or applications generating logs. They'll transfer that data to their cluster using technologies like Flume or Scoop, land the data in files on HDFS, and then have a processing loop around it. This is a really great architecture, except that it's inherently pretty latent. You have a pretty big amount of time between when data lands on your storage system to when it's available for processing. So that's not ideal when you want to get real-time insights on your data. If you compare that to a stream processing system, things look relatively similar. The main difference is you've got a system, typically Kafka, but there are others out there, that acts as a publish and subscribe message bus in between your data producers and your data consumers. And in this case, data consumers can read the streams directly out of Kafka rather than having to wait for them to be materialized on disk as files on HDFS. You also often have just custom Kafka consumers. Not everything that you do has to happen inside of a stream processing framework. You don't necessarily have to write a Spark streaming job if all you want to do is take in data and write it to your sort of Hadoop data warehouse so that you can then process it in batch. But often you want to split that stream so you can get some real-time insights on some of the data while still storing bulk data for later analysis or further analysis. So I'm going to focus a little bit more on this stream aspects of this, specifically the stream processing frameworks that folks frequently use, and some of the different phases of stream processing and what that means to people that are building analytical solutions on top of this kind of an architecture. This is going to be a really, really quick overview. If you're really interested in stream processing, there are some great blog posts by the team that built Apache Beam, which is an API, a generic API for multiple distributed stream processing systems. That's on the O'Reilly blog. Really great overview of stream processing, how it differs from batch, They actually reduce batch processing to a special case of stream processing with just really large batch sizes and really longer, really big delays between when the data is produced to when the results are available. So the way that I break down stream processing is kind of in the different operations that you're going to apply on the stream. You've got filtering, which is dropping the stuff that you don't care about. You have extraction, which is taking quote-unquote raw data and turning it into structured data. It turns out most of your raw data does have a lot of structure. It's just that structure is often presented to you as a bag of bytes, and you have to sort of do some extra parsing before you can reuse the structure of that data more efficiently. Projection is basically what happens when you run a select query on your database. It's all of the columns that you're actually selecting, or in some cases, you may be taking nested records and flattening them for particular purposes, either for storage or for analysis. Aggregation, which sort of implies grouping and time windows. That's really key for any kind of real-time log or metrics analysis. You need to see numbers in real time, aggregated over time, in order to make intelligent decisions about what's happening in your infrastructure. Joins, you may either be doing something more like an enrichment, which is where you've got a small reference data set, and maybe your stream of data has just ID numbers in it, and you want to get sort of a rich version of that ID into your stream or into your records. That's a kind of join where you're really just doing data enrichment, or you may be actually joining multiple streams together, where you have to worry about details like how long do I wait for the second stream to show up before I decide that there may not be a record to join on this one that I've already seen. And then this all leads into very advanced data modeling, all the fun data science stuff that everyone wants to work on. I'm going to really focus on these first three. The reason for that is they're really critical for any of the rest of the analysis. If you don't get these right, you're not going to get to the point where you can create useful models on your data. And I sort of lump these together into what I call data transformation, sort of the classic T part of ETL. So now I'm going to take a brief sidestep to talk about some of the existing systems out here for doing stream processing. They're all good. This is just meant to be a very quick overview. I'm not going to go into a lot of depth. So I would definitely recommend looking up their websites and projects in order to get some more information about how they work and how they maybe differ. So Storm describes itself as a distributed real-time computation system. It's a very generic description, but it's just a fancy way of saying that they try to take data and process it as it comes. The way that they organize their applications or their jobs is what they call a topology. So topology is analogous to a MapReduce job in the batch world. Topologies operate over streams of tuples. That's their word for a record or an event. I'll use any of those words interchangeably. They've got specialized components that act as sources of streams or sources of streams of tuples that they call spouts. And then they have arbitrary operations that they call bolts that are basically what happens in between a spout and the ultimate data sink. And those can be arbitrary operations. They can be the things like the filtering and the aggregating or the joining that I talked about earlier. Or there may be some custom function that you just want to run over every record. Think of that about that like the map phase of a MapReduce job. Oh, and I should mention Storm's the oldest open source stream processing engine, or one of the oldest ones, being the ripe old age of about 5 years, I think. Apache Spark is a little bit newer. It's a little bit more hyped at the moment. It supports both batch processing and stream processing, which is one of the reasons why it's very popular. They have a slightly different model for streaming. Some people argue that it's not streaming. I think it still is. They take a continuous stream of records and discretize it into what they call a D stream or a distributed stream. The main difference between the way that Apache Spark is presenting the stream of data to you and the way that Storm does is Storm presents every record or every tuple as it comes in, whereas Spark always gives you a micro batch. You can set your micro batch size to 1, in which case you are doing effectively record at a time processing, but it's really designed for higher throughput and having your data come in small batches for you to process as a stream, rather than necessarily doing record at a time processing. Apache Flink is a newer open source project that's gaining a lot of speed. It also both supports batch and stream processing. One of the neat things about Flink is that the batch processing engine and the stream processing engine is actually the same engine. They view batch as just a specialization of the stream use case, where the source of your stream are files on disk, rather than like a network socket or something like that. They call their records or their stream data stream, which is an unbounded collection of records. Again, records, tuples, events, all kind of the same thing. Operations can apply to individual records or windows of records. One of the things that they do in Flink is they make windowing, especially time windowing, a sort of first-class function, because that's a very common operation when you're doing any kind of stream processing. And even when you do batch processing, you're probably doing it on windows of records. You just don't think of it like that. If you ever have a system that's pulling in, say, log data and writing it out to directories where each directory is named for the day that the logs were produced, that's basically a window. You've created a daily window of your data. It's just you're waiting for that day to sort of fill up before you run your batch reports on it. Whereas with the stream processing systems, you can do much shorter windows in order to get results quicker from when they're produced. Flink also supports record at a time processing like Storm does, and unlike Spark does, although Spark you can kind of fake it to do that. I also want to give a shout out to Kafka. I mentioned it on an earlier slide. Kafka itself is not a stream processing system. It's a pub subsystem that's implemented as a distributed commit log. It's very popular as both a source and a sink for any of these stream processing frameworks. The reason for that is it gives you very high throughput. It's very scalable, gives you strong durability guarantees, and very easy to understand delivery guarantees. It's very easy to configure Kafka to give you at least once delivery. That means that you won't drop any messages, but it's possible that you may receive duplicates. There's also a lot of work going on to enable exactly once semantics, so that if you really care about the consistency of your results, you can make sure that your stream processing is being fed by an exactly once stream. You can do stream processing directly in Kafka consumers. We actually do that at Rakhana for a lot of our stuff. We don't have to do a lot of fancy processing with it. And so when your needs aren't that complex, you may not need to reach for an Apache Spark or an Apache Storm. And you may actually just build your stream processing logic directly into your Java daemon, which is reading out of Kafka. There's also a newer addition to the Kafka family called Kafka Streams, which is like a stream processing library. It is a competitor to these other streaming systems. It's very new. I don't know a whole lot about it, but the folks that wrote Kafka are pretty smart, and so they also wrote this. All right, so let me get back to data transformation. So just as a reminder, filter is the sort of first stage of data transformation. That's where you're basically taking your stream of records that are coming in all sorts of different colors and dropping everything but the blue records, because blue is the best color. Extraction, this is where you've got data coming in where you just have sort of a binary blob of data. That binary blob is actually a string, which has the sort of typical Apache log standard or the common log format. But you want to be able to represent that in a more structured manner. So you're going to extract fields from this body and turn it into attributes in some kind of an event schema. And then projection, I lump projection in with flattening. In this case, we're taking the same event after it's had data extracted from it that we saw on the previous slide, and we're taking a few of these fields, both sort of top-level fields and nested fields, and turning them into all top-level fields in some new schema. So this is very common. So in our system, we serialize all of the data using Avro. And in fact, we use a single Avro serialization or single Avro schema for all of our event data. And I'll go into a little bit more about our data model in a little bit later. But it's very common for our customers to want to be able to take that data, which is in a nested format like this, flatten it out for certain specific data sets, and be able to throw like a Hive or an Impala at it to do ad hoc SQL queries on top of the archive of data. So what's the problem? You've got these great stream processing engines. You know that you need to do data transformation as sort of the first phase of your stream processing. Why do we, what's the issue here? And it really comes down to when you think about who needs to do the transformation, especially in stream processing. Yes, you've got your regular software developers. They can pretty much work in any framework. You've got data engineers and data scientists, which are mostly thinking about what features do they want to extract out of the data. Sysadmins may need to ETL data before it goes in. Or you may just have business analysts, which aren't really people that are going to go down and write code, but they do want to configure sort of custom transformations that will always apply to the data before it ends up in their backend systems. So what are the tools that people use? So if you're using any of those stream processing frameworks, you're sort of stuck in one of these three languages. And again, if you're a developer, that's great. These languages are awesome. You probably love at least one of them. Or if you're like me, you hate all of them. But it means that every time that you need to do any kind of filter, extraction, or other kind of data transformation, you're going to be sort of writing custom logic in whatever language you have to reach for. The other thing is, what if you want to experiment with these different stream processing systems? You have to rebuild your logic using the APIs and primitives that they provide. So you can't take like a Storm Bolt and run it inside of an Apache Spark application as an example. And really where this stuff meets the road is in feature engineering. Feature engineering is what Josh Wills calls the dark art of data science. He defines feature engineering as getting a mess of raw data that can be used as input to a machine learning algorithm. And the dirty secret of data science is that like 95% of the work is in doing this. It's in taking that raw data, pulling out what you need from it, building the features that actually have meaning that can help model your data, and then putting them into the very fancy data modeling algorithms. The data modeling algorithms by themselves are pretty useless if you haven't extracted the right features from the data that you want to model. So what's our proposed solution? You want something that you can embed in any of the stream processing frameworks. You want something reusable, and you want something accessible to audiences wider than just software developers. So what we've built is something that we call Rakhana Transform. It's a Java library. You can embed it in any JVM application. All of the stream processing frameworks out there support Java or run on the JVM, so you can embed it in any of those. It's built on top of another library that we've built called Rakhana Configuration. Rakhana Configuration, all you really need to know about it is we started with JSON, which is nice because it's nested. We added the ability to comment because you can't have a configuration file without comments. We added support for specific numeric types because calling all of your numbers just a number is really, really bad. And then we remove sort of the excess quoting that JSON requires. So you'll see some examples of this a little bit later. So again, I promised I would tell you a little bit more about our data model. So we view everything coming into our system, whether it's a metric or a log message, as an event. The real key fields here are time. Every event has a time stamp on it. That's why window processing over events streams is very important. They also have a globally unique identifier. We actually build those identifiers based on a hash of the contents of the event. So if you modify an event, you, by definition, create a new event. Every event has a type ID. That's so that we can apply sort of additional schema information about events without having to change the serialization format. So we've got one Avro schema for everything, but we can make some determinations about what attributes we expect or the format of the body of an event. These next three fields are really geared towards our IT operational use case. So location is like a rack or a data center ID. Host is the host name or IP address that generated an event. And service is the service. So the service could be like Hadoop HDFS, or it could be MySQL. Or it could be something that's more generic, like your CRM system, which actually consists of multiple different components. The body is just a raw byte array. We don't interpret the body other than in the context of the event type IDs. So we let you stuff anything into the body of an event that you want. And then we have attributes, which are string key value pairs for all of that sort of enriched data, or for sort of more detailed information about your events. And the attributes are arbitrary, so you can add any key value pair you want without having to register it with a type system or something like that. So here's an example event. Again, the events are all serialized in Avro. I'm showing it here in JSON just because it's easier to view that rather than showing you a bunch of bytes. So the ID is a hash of the rest of the contents. You've got a timestamp in there, which we report in milliseconds since the epoch. Type ID, all these other things. This is an example of a syslog event. So this is the sort of raw syslog packet. And then here are the different syslog fields that we're pulling out of it, the host name that generated the event, the actual syslog message, the severity and the facility that gets parsed out of here, and then the syslog timestamp, which may or may not match the event timestamp. As you're getting events into the system, you may be initially tagging them with a raw timestamp of when you saw the event arrive, and then you may be reprocessing that event to extract the timestamp that was actually in the record in order to replace it and generate a new event. So I'm going to show you a couple of examples. The first example is a filter, extract, and flatten use case. So what you want to do is filter out events that don't have the event type ID of 100, filter out events whose host name doesn't begin with the letters EX, and then extract a numeric prefix from the syslog message, and then flatten the syslog attributes and top-level fields into a different Avro schema. The real use case here is that you want to bring in certain types of syslog messages and ultimately feed them into a table that you can then process with your SQL data tools. So this is what the transformation looks like at a high level. So this is that Rakhana configuration language that I was telling you about. Load event is just a way of taking the sort of raw event input and exploding it into some variables in the global context space that the rest of the transformation actions are able to take advantage of. Filter does exactly what you would expect. It only lets through things that have the specified event type ID. Extraction happens with regular expressions. And I'll go into more details on that in a second. We do a second filter after the regular expression extraction to look at the host name. And you'll notice that this variable here sort of calls back to something that'll be in that regular expression. We do a second regular expression to extract the numeric prefix. And then finally, we build the final Avro record, and then we accumulate the output. So the overall data model or processing model for the transformation engine is one event goes in and 0 or more events go out. So zooming into extracting the hostname prefix, we're applying a regular expression that just looks at the first 2 characters. It's going to pull those first 2 characters from the syslog hostname, and then it's going to put it into this destination. Destination isn't really a great name for that because it's actually a prefix for variables. So basically, all of the matching groups that you had in the regular expression will become variables that look like this. There's also a variable for did the regular expression match or not. So group 1 is the first set of parentheses there. There's also a group 0, which is implicitly the entire string that matched. So if you want to extract the entire string, you can do that. Extracting the numeric prefix is very similar. It's another regex action. In this case, we're just looking for 0 or more digits at the beginning of the syslog message. The other thing that this shows is some powerful sort of flow of control you can have inside of your regular expression matching. Match actions is what gets executed if the regular expression matched the pattern. And no match actions is what happens if there wasn't a match. So if the regular expression didn't match the pattern, you'll end up triggering this case. Building an Avro record is fairly simple. Basically, all of the fields for your Avro record go into the left side of the field mapping here. And then the values are these variables that you're extracting from the original event. And then you reference the schema so that we know how to construct the object that you're building. So the second use case I think is actually more interesting because it's something that our customers do all the time, which is we've got metrics that our system will collect natively from like your CPU and memory and things like that. But you also have a ton of metrics that end up in log data. And you want to be able to extract that out and actually turn that into top-level metrics that the system can interpret and apply any of its analytics against. So in this case, the input's going to be HTTP status logs. We're going to extract the request latency, so the amount of time that the HTTP request took. We're also going to extract counts by HTTP status code. So if you have an HTTP response of 403 or 400 or 200 or whatever it is, you want to count every event that had that particular status code. Real quick, the way that we break down metrics is into two broad metric types. One is a gauge. That's a value that varies over time. You can think about it like your speedometer on your car. You look at the speedometer, it tells you the speed that you're currently going. But if you stop paying attention to it and look at it again 5 minutes later, it could just say a completely separate speed. The other is a counter. A counter is a way of accumulating data over time. So if you want to count events that have a particular attribute or have a particular pattern associated with them, you can take in the event and basically output a count of 1, and then our system will aggregate those counts together into different time windows on the back end for you. Like I said before, our metrics actually get serialized as events on the wire. So this is what a metric event looks like. It's got all the same things that any other event has. And then the way that we represent the metrics themselves are as attributes. So on the left-hand side, there's this m.dot prefix. That tells our system that this is a metric attribute versus another type of attribute. The rest of the attribute name is the actual name of the metric. And then on the right-hand side is the value followed by the pipe character and then the type of metric. So G for gauge metrics and C for counters. So this is what the transformation configuration for extracting metrics looks like. Again, we load the event. Then we're going to first build a gauge metric for HTTP request latency by pulling out the latency attribute and converting it to a double. We're going to store that into a latency metric variable. We're going to capture that to our output because we want all of the metrics from this, not just a single metric. And then this is a little bit more interesting. This is our way of doing more dynamic events. In this case, we want to do http.status.statusCodeNumber.count. So this is actually extracting the HTTP status code value from the log data and putting that into the name of the metric. So you're going to get a metric for 200, a metric for 400, a metric for 403, so that we get a unique count for each of those different status codes. And again, we pull that out, and then we're just going to always assign this a value for 1, because by definition, if we see this in a single log message, it means that we've seen it one time. And again, copy that to output variable, and then make sure that the output variable ends up in the output of the transformation config itself. So I'm going to go a little bit more in depth onto the architecture of the transformation engine. Not going to go super into it, but if you have questions later, I'm happy to answer them. So like I said, the transformation engine, the transformations themselves are represented as those configuration files using that JSON-like syntax. When you parse the configuration, we actually bind that configuration and generate all of the Java objects that we're going to need at runtime. So at runtime, we're actually doing no dynamic configuration lookup. This means that the transformation engine is very fast. It's able to take your configuration file and basically turn it into something very close to if you were handwriting custom Java code to do that processing yourself. The engine itself doesn't actually operate just by itself. It needs sort of this driver program. So we've got a standard driver program that we run in sort of all of our Kafka consumers and other processing contexts. But this is what would be custom for a particular stream processing engine. So if you wanted to embed this library into Spark, you would just need a Spark driver that was able to sort of coordinate the parsing of the configs and then some of these other steps here. So the driver, after the configure is parsed, it's going to initialize the context. The context is how we provide data or send data between different actions. So it's really just a global variable list. So there are key, string keys, and object values. So any of those variables that were referenced in the transformation configurations are all stored in, this global context. So initialize the context. This is also where you would copy in the input. So the driver is responsible for taking the input from however it got the data into the context. It then calls a global run on the root action, and then that kicks off the rest of the processing. So once it executes that root action, all of the other processing and flow of control is dictated by the configuration file itself. As the actions are executing, they're going to read and write variables from the context. And then finally, when the final action is done, the driver will copy any output. So that's what the accumulate output action is for, is to put it into a well-known location for the driver to copy the output out from. We also do support custom actions, so you can write your own actions in Java or any other JVM language using the Java Services Framework. That means that in order to register your action with the library, you just have to drop a jar on the class path. You don't have to do anything else. There's no special registration that you need to do there. Custom actions also appear as top-level keywords. In fact, all of the actions that we have built in with our library are also registered using the Java Services Framework. So there's no actions that are given like special privileges or keywords that are given special privileges. Everything is fully dynamic based on what's on the class path. And then there are two interfaces that you have to implement classes for. One is the action interface. That's what actually does the processing, and the only required method there is the execute, which is to actually run the action. And then we have an action builder interface, which constructs those action objects. The action builder interface is what ends up binding to the configuration language. And we do that with Java annotations. So you just annotate the builder set methods with the key that will represent that. And then the build method takes all of those values and creates your actual action instance of your action class. So some examples of custom actions that we or our customers have built. A lot of it's for custom log formats. Not every log format works well with regular expression as the parsing engine. So a lot of our customers will write custom parsers, build them as actions, and then that way they can parse any sort of arbitrary log format that may be coming into their system. Another one is enrichment. So the most popular one is looking up IP addresses in a GeoIP database and adding that data to the events coming through. And then there's other reference data set lookups that they'll do, like device ID to device name mapping. So kind of pulling it back together. Stream processing sort of changes the way that you think about data analysis. You no longer think about it in terms of just landing my data in a file system and then trolling through it. You start to think about the real-time aspects of it and all of those considerations. But the data transformation aspects of stream processing, you really want to be given to the widest audience available. The more that you hold that back to just a few people, the more expensive your stream processing systems are actually going to be. You want to reduce your reliance on developers for coding custom pipelines. Also, your developers probably don't want to code the same data transformation in 5 different places for 5 different customers. They want to kind of do it once and then just hand them over the configuration file. Another really cool thing that you can do is you can reuse the same configuration that you do on your stream processing system as you would on a batch job. So one of the things that we're looking at is our system, since we're doing log collection, it of course supports log search. Sometimes you want to process the results of the log search after the fact, so you may not have known how exactly you wanted to extract data from it when the data was coming into the system. And so you actually want to apply this kind of transformation configuration on the back end at query time so that you can extract things before presenting it to the user in the user interface. So this is not yet publicly available. We are wrapping it up and going through our process to get it released, but it will be released soon under the Apache software license. The configuration library that I mentioned is available today as open source, so you're free to check that out. Use it for your own applications if it's something that's useful or interesting to you. And with that, I've got a few minutes for questions. Yeah, there's a question right here.
Do you have any consideration for inter-event transformations, or is it all just within one event?
Great. So the question was, is there any consideration for inter-event transformations? And the answer is right now no. So we do it all for event at a time processing. What is very common is to take a single event and turn it into multiple events. For example, some of our customers have events which are actually these complex JSON objects that actually contain multiple individual records in them. And so we'll parse the JSON, turn each individual JSON object into a separate event, and then output those. But as far as inter-event processing, it's not designed for that. There's a question in the back.
I have a two-part question. You mentioned the different streaming platforms. Do you use one over the other? Is there different use cases, like Storm versus Spark?
Mm-hmm.
And have you considered writing a driver for Apache Apex streaming platform?
Apache Apex was the last part. So the question was, do we use any particular stream processing platforms ourselves? We are using Spark for some of our internal stuff. The main motivation factor for us was access to MLlib. Spark has sort of the best machine learning libraries of the stuff that's out there. So we haven't written a driver for Apache Apex, but would love to chat with you, especially once this is open source, to be able to have more drivers for different systems out there. We have a question up front.
How do you deal with large file-based logs? Do you guys turn those into streams, or what do you do?
Yeah, so the question was, how do you deal with large file-based logs? The part of our system that takes log files and turns them into events is our data collection agent. So you configure that with either a sequence of bytes that delineates records, or like a regular expression to delineate records. And then it's going to take those large files, turn them into individual events, and then send those events directly to Kafka.
Is that something you got to put on the customer's platform, or you just suck the file over to your own platform?
So typically it's put directly on the customer platform, mostly because that means we also collect host metrics. But there's nothing that prevents you from setting up one of our agents on a central server and pushing the files to that server via FTP or some other file transfer protocol, and then sort of doing all of the bulk file to event transformations in a central location. Another question up here.
If I want to do a database lookup in the extraction process, is the configuration supports to connect to a database?
Yeah, so the question is, does the transformation support looking things up in a database? We don't have a generic action for that, but like that GeoIP lookup custom action does that with the GeoMind database. And there's a couple of other custom actions that our customers have done to do that. Typically, one of the things that we'll do is we'll throw an EH cache in front of like a JDB source so that you're getting a good caching effect and that you're not necessarily going to the database on every single record lookup. Because if you've got millions of events coming in per second, you probably don't want to generate millions of events of additional transactions on the server, yeah. All right, thank you very much.